In this video, we are going to apply the Bernoulli equation into one of the fluid flow device called as Venturi meter. The Venturi meter basically is used to measure the velocity and rate of flow, and this Venturi meter cause very low head losses, and thus they should be preferred for applications that cannot allow large pressure drops, but it is more expensive than other device such as orifice. So in this Venturi meter, it always usually connected with the manometer to measure the pressure difference. So this is the manometer, and then this is the Venturi meter. Okay. Right, so this is the inlet. Example, we have diameter 1 here, and this is the diameter 2. Okay, and then this manometer basically can be used any kind of fluid that usually we use are manometer mercury. And let's say here is water flowing from point 1 to point 2. Okay, so at point 1 basically we have some pressure P1 and also V1 as the velocity, and at section 2, at the throat section, we have P2. Sorry, I put here P2 and also V2. Okay, we are going to apply the Bernoulli principle into this Venturi meter, but you need to put also the head here. Okay, and also this is the middle section. This is A. So if we want to apply the Bernoulli equation from point 1 to point 2, there are also other unknown that we need to consider. So we need to consider at least 2 or 3 equations to solve the Bernoulli equation. At first, we will write all of the parameter in the Bernoulli equation. Here P1 over rho g plus V1 square over 2g plus Z1 equal to P2 over rho g plus V2 square over 2g plus Z2. So we need to put some of our assumption here. Basically, because this flow occurred inside a device, or we call as the internal flow, the pressure at the inlet and also at the outlet cannot be neglected, and also with the velocity. However, we know that from this diagram, you can see that the level here Z1 is equal to Z2. So we can cancel out Z1 and also Z2, and then we will arrange the equation P1 minus P2 over rho g equal V2 square minus V1 square over 2g. So we have 4 unknown: P1, P2, V1 and also V2. So by using the manometer relation between point 1 and also point 2, let's say we start at P1 here. Okay, this P1 at this location 1, and at the middle section here we put 2. P1 go downward, it becomes plus rho of the water, and then this is rho of the mercury, G A plus hash, and then you go upward minus row of the mercury G hash, then you go upward again minus row water G hash, sorry, A, this is equal to P2. So now we will write this equation in terms of P1 minus P2. P1 minus P2 equal to negative rho W GA minus rho W G hash plus rho M G hash plus rho W GA. This is equal to, this can be cancelled out, G hash rho mercury minus rho of the water. Then we can replace into the Bernoulli equation here to simplify the problem. But before that, we also need to apply the continuity equation from point 1 to point 2 to reduce other unknown. So here, if we apply the continuity equation, so this is the manometer, this is from the continuity equation. We will try to apply it from point 1 to point 2. So from the continuity equation, A1 V1 equal to A2 V2. So we will write V2 in terms of V1. V2 equal to A1 over A2 V1. Okay, now we will put our continuity equation. This is equation 1, this is equation 2, this is equation 3. We put 2 and 3 into 1. What we will get is G hash rho mercury minus rho of the water divided by rho G equal to V2 square A1 over A2 V1 square minus V1 square divided by 2G. So our target is to get what is the V1 and also V2, because this Venturi meter is used to measure the velocity, and then we can calculate the volume flow rate. So in this case, I will rearrange V1. This will becomes V1 square bracket A1 over A2 square minus 1 right. So on the left hand side here, it will becomes 2G hash over rho of the water rho M minus rho of the water. So this is rho of the water because we apply the Bernoulli at water. So here, what is your V1? It will becomes V1 square equal to 2G hash over rho W rho M, or we can write density on the one terms here, 2G hash rho M minus rho water, then this divide by A1 over A2 square minus 1. . Okay, we can simplify more. Equal to 2g hash, this is rho mercury over rho water minus 1. On the denominator we can change into a1 square minus a2 square over a2 square. Okay, and then if I put here v1 square and I want v1 only, what we will get is, so this comes to g hash rho m over rho w minus 1 multiply with a2 square. This is becomes a1 square minus a2 square. So your v1 is equal to the square root of 2g hash rho mercury over rho of the water minus 1 divided by a1 square minus a2 square. Then here we have a2. Or you can divide by, spread it in term of area, a2 over square root of a1 square minus a2 square square root 2g hash rho m over rho w minus 1. So this is the velocity at point 1. Okay, in order to get the velocity at point 2, you can connect it with continuity equation and you get the different kind of formula. Okay, how about the flow rate? The flow rate, and then we just need to put, or we modify from this v dot 1 equal to a1 v1, so that you will get a1 a2 over square root a1 square minus a2 square square root 2g hash rho m over rho water minus 1. So this is the volume flow rate, and the volume flow rate is considered to be constant throughout the section. Next video we will apply this equation into a simple example.